Hello my dear students, today we are going to see some more interesting topics from unit number 3, that is diagonalization. So first of all, we will recall the definition of symmetric matrix that is required. So we already know actually what symmetric matrix is. So a square matrix A is said to be symmetric if A is equal to A transpose, or you can say Aij is equal to Aji for all I and j. Just note a few things regarding a real symmetric matrix. Eigenvalues of symmetric matrix are always real. Means whenever you are having some symmetric matrix, and if you try to find the eigenvalues of that, whenever I say symmetric matrix, I mean real symmetric matrix. What do you mean by real symmetric matrix? The entries of that matrix will be real. Okay. So the eigenvalues of such matrices are real. They will not be imaginary. Okay. The next thing is eigenvectors corresponding to distinct eigenvalues of a real symmetric matrix are always orthogonal. I mean, suppose you are having some real symmetric matrix, and suppose you find some eigenvalues of that, and suppose eigenvalues comes out to be 1, 2 and 3, then whatever the eigenvectors will be there, x1, x2 and x3. Okay, so all these eigenvectors will be mutually orthogonal. What do you mean by orthogonal? Two vectors are said to be orthogonal if their inner product is equal to 0. So I mean inner product of x1 with x2 will be 0, inner product of x2 with x3 is going to be 0, and inner product of x1 with x3 is also going to be 0. You already know how to find the inner product. Suppose I am having two vectors, x1 say 1, 2, 3 and x2 say 1, 1 and minus 1. So what will be the inner product of x1 with x2? So this inner product is going to be, simply take the dot product of the corresponding elements and add them. So 1 multiplied by 1 is 1, plus 2 multiplied by 1 is 2, plus 3 multiplied by minus 1 is minus 3, and this is equal to 3 minus 3, which is 0, and therefore we will say that this x1 will be orthogonal to what? X2. I hope you got what I have done here. Okay, so this is the meaning of the result. Therefore the eigenvectors corresponding to distinct eigenvalues of real symmetric matrix are going to be what? Orthogonal. Okay, just keep it in mind. Now we are going to see a new concept, that is orthogonally diagonalizable matrix. Okay, so a square matrix A is said to be orthogonally diagonalizable if there exists a orthogonal matrix P such that P inverse AP is equal to what? A diagonal matrix. I mean A will be orthogonally diagonalizable if A is similar to diagonal matrix, no doubt about that, but in addition to that, whatever this non-singular matrix exists, that non-singular matrix should be what? Orthogonal. Now what do you mean by orthogonal matrix? Now we have already seen the definition of that. A square matrix is said to be orthogonal if A inverse is equal to A transpose. Now you already know what is the determinant of orthogonal matrix. It is plus or minus 1. So while discussing the orthogonal matrix, why the matrix is called as orthogonal? Because the rows and columns of that matrix are what? Orthogonal to each other. I mean 1 upon square root of 2, 1 upon square root of 2, minus 1 upon square root of 2 and 1 upon square root of 2 is going to be a orthogonal matrix, because if you see the columns of this matrix are going to be orthogonal to each other. I mean if I take the dot product, 1 upon root 2 multiplied by minus 1 upon root 2 will be minus half, plus 1 upon root 2 multiplied by 1 upon root 2 will be half. This will be equal to 0, isn't it? And observe one more thing, that what is the norm of each vector? What do you mean by norm actually? So if your vector is somewhat x1 x2, what is the norm of that? So norm of the vector is given by under root of x1 square plus x2 square, right? We already studied it in second year. So in over here, what will be the norm of first column? So norm of first column will be under root of 1 upon root 2 square plus 1 upon root 2 square, and you can observe that it is going to be 1. Similarly, norm of this second column is also going to be 1, and similar thing will happen for rows also. So rows are also going to be orthogonal to each other, and norm of each row is going to be 1. So these are the basic properties satisfied by an orthogonal matrix. Obviously A inverse is going to be equal to A transpose, you can check, because what will be my A transpose in this case? It will be 1 upon root 2 minus 1 upon root 2, 1 upon root 2 and 1 upon root 2. and if you take the product, you will observe that you will get the identity matrix. Let us try it. 1 upon root 2 multiplied by 1 upon root 2 will be half, and minus 1 upon root 2 multiplied by minus 1 upon root 2 will be again plus half. Next, 1 upon root 2 multiplied by this 1 upon root 2 will be half, and minus 1 upon root 2 multiplied by this will be minus half. Similarly, over here I guess we will get half minus half, yeah, and over here you will get half plus half, and you can see it is the identity matrix. Similarly, you can check that A transpose A is also the identity matrix, isn't it? So just focus on this note, very important. Whenever you talk about a real symmetric matrix, it is always orthogonally diagonalizable. It means you will be able to find the orthogonal matrix P such that P inverse AP will be equal to what? A diagonal matrix.